The universe is constantly expanding, stretching farther and farther beyond what we can observe. Yet a question lingers in the depths of our curiosity. If nothing exists outside the universe, then what is it expanding into? This mystery challenges the very limits of our imagination and understanding. Is space itself growing, or is our perception of it changing? Join us as we journey to the edge of existence, exploring one of the most profound questions in cosmology: what lies beyond the universe, if anything at all? Hold that question in a quiet corner of your mind as we move gently forward. The universe is expanding, yet not into a room beyond itself. In our daily lives, everything grows into something: roots into soil, a town into open fields, a splash into air. So our first picture is a balloon swelling in a living room, rubber pressing against the air and furniture as it grows. That image feels right because there is a clear outside, a container that allows the balloon to become bigger. But space does not behave like a balloon in a room. There is no cosmic living room, no outer wall, no warehouse of emptiness waiting to be filled. When we say the universe expands, we mean the very fabric we call space is stretching from within. It makes room by being the room. If that sounds strange, you are in good company. Even great thinkers stumbled here. A gentler way to picture it is to imagine drawing a circle that is too large for your paper, and instead of finding a bigger sheet, the paper itself grows as your pencil moves. In the world we know, that cannot happen. Yet in the world of the cosmos, the paper is space, and it can stretch to fit what it holds without needing an outside at all. This is why the old riddle, "What is the universe expanding into?" slips out of our hands like sand. It is a bit like asking what lies north of the North Pole. On a globe, north has meaning until you reach the pole. Past that point, the word north stops fitting the map. In the same way, outside stops fitting the universe. Astronomers learned this not by guessing, but by watching. When Edwin Hubble and others measured distant galaxies, they found that the farther a galaxy is, the faster it seems to be rushing away. At first glance, that looks like fragments from a single blast racing through empty space, as if we sat at the center of a cosmic firework. But that picture fails, because every galaxy would draw the same conclusion from where it sits. No seat is special. The better understanding is calmer and more elegant. Space itself is stretching, and as it stretches, the distances between galaxies grow. Think of tiny dots painted on the surface of a balloon. As the balloon inflates, each dot sees all the others drift away along the surface, even though the dots are not crawling anywhere. There is no dot at the center of the surface. The whole surface is the thing that's growing. Now, trade that two-dimensional skin for the three-dimensional space you live in. The increase in distance is real, but it is driven by the growth of space itself, not by galaxies flying through some larger room. Light carries this story to us with quiet honesty. When a distant galaxy sends out light, each wave leaves with a certain wavelength, like a color signature. As that light crosses the universe, the space it moves through keeps expanding. Picture yourself walking across a moving walkway that slowly stretches under your feet. Your steps are steady, yet the ground is lengthening as you go. For light, the result is not longer steps but longer waves. By the time those waves reach our telescopes, they have been pulled out, shifted toward the red end of the spectrum. We call this cosmological redshift. It isn't the same as the sound of a passing ambulance changing pitch because the siren is moving through still air. Here, the air-space itself is changing while the light travels. This is one of the cleanest clues that the expansion is not a story we tell ourselves. It is baked into the light. There is a simple number that helps the mind anchor to this idea. For some of the most distant galaxies we can see, the light that left them long ago has been stretched to roughly 40 times its original wavelength. Radiation that began as sharp ultraviolet now arrives as gentle infrared heat. A factor of 40 is not a small tweak. It whispers that the universe grew vastly during that long crossing. When that ancient light set out, the cosmos was much smaller than it is now, and the place that would become the Milky Way was much closer to those early galaxies. We are not watching dots drift away in stillness. We are watching the stage itself widen between them, again and again, like bread rising in a warm kitchen. This widening is not somewhere far off. It is everywhere at once. Even the space in this room would like to join the stretch. The reason you do not notice is that local forces hold things together. The pull between charged particles, what we call electromagnetic force, binds atoms and molecules with a grip far stronger than the slow, steady expansion of space. Gravity binds planets to stars and stars into galaxies. Within these systems, the expansion is too weak to win. Only across very large distances, where no great forces are holding objects together, does the quiet stretch add up. If you return to the bread image, galaxies are like raisins in the dough. The raisins are not swimming outward. They are carried apart as the dough rises. The spaces between clusters of raisins grow, while each raisin and each small group stays intact. This is also why the question, what is space expanding into, keeps missing the mark. In the bread picture, asking that is like standing inside the dough and demanding to see the kitchen air around it, as if you were not already part of the loaf. From our place inside the universe, the idea of an outside is not useful. The coordinates that would point to it do not exist within the system. The universe is not expanding into something else. It is expanding by changing the distances defined within itself. That is a quieter thought than it first appears, and it fits the evidence we gather from light across the sky. Even Einstein wrestled with this. His first models of the universe tried to hold things steady, because a changing universe was a hard notion to accept. Later, the evidence pulled the theory into line with what the sky was saying. The redshift of galaxies, mapped over many years and with many tools, points to the same patient truth. The fabric grows. It does not need walls to push against. It does not need a larger hole. It only needs the rules that govern space and time, and those rules allow the distances to swell. Because this expansion acts everywhere, it also shapes what we can see. Light has a finite speed, and the universe has an age, so there is a limit to how far its messages can reach us. While that light travels, space keeps stretching, making the trip even longer. Some signals are softened and slowed until they will never arrive. In that sense, we live within a kind of horizon, a soft boundary drawn not by bricks or borders, but by time itself. Beyond it, the story continues, yet its pages have not had time to reach our hands. When you step outside at night and lift your eyes to the stars, it is easy to feel as if the whole story is there, written across the dark. Yet the sky is only a small window. We live inside an invisible sphere, our observable universe, with a radius of about 46 billion light years. Beyond that soft edge, the universe keeps going. More galaxies, more stars, more quiet places where light is on its way but has not arrived. This limit is not a wall. It is a boundary set by time and by the speed at which light can carry news. Light does not jump, it travels. When you look at the sun, you see it as it was 8 minutes ago. The nearest star system, Alpha Centauri, appears as it was roughly 4 years ago. The Andromeda galaxy greets you from 2.5 million years in the past. Farther always means earlier. The deeper your gaze, the older the message you receive. Now fold in one more piece. The universe has an age, about 13.8 billion years. That means the oldest light that can possibly reach us has been traveling for 13.8 billion years. If a galaxy stood farther away than light could cross in that time, its signal would not yet be here. But there is a twist. Space has been expanding while that light traveled. A galaxy that sent its message when it was much closer is far, far away by the time the message finally arrives. Because of that stretching, Our observable radius is not 13.8 billion light-years, but about 46 billion. We see the glow from long ago, yet the places that sent it now sit much farther away. In that sense, our view is like a family album, precious, detailed, and always a step behind the present. It can help to imagine standing in a morning fog. You see a circle of ground around you, clear and real. You know the meadow continues beyond the mist, even though you cannot see it. The observable universe is that clear circle, and the rest is hidden for now. We cannot point a telescope through the fog and force the light to arrive faster. The speed of light is about 186,000 miles per second, the fastest speed there is, and time moves at its steady pace. Those two facts shape the size of our view. If the universe is truly infinite, then any finite bubble, no matter how vast, covers effectively none of the whole. That sounds severe, but it is simply a reminder that our window is local, not total. The oldest light our eyes can ever receive is already here, washing over us from every direction. It began its journey when the universe was only about 380,000 years old. Before that time, the cosmos was a hot, glowing sea of charged particles, protons and electrons so dense and lively that light could not travel far without being absorbed or scattered. We call that early state a plasma. In such a world, the universe was opaque, like trying to look through the body of the Sunday. As the universe expanded, it cooled. When it became cool enough, protons and electrons found each other and paired up to make the first simple atoms, mostly hydrogen. With fewer free charges, the fog lifted. Space became transparent. The first photons, little packets of light that slipped free in that clearing, have been on the road ever since. They reach us today as a gentle microwave glow called the cosmic microwave background. If you could tune an old television to a blank channel, a tiny part of the static would be that afterglow. It is faint, even-tempered, and everywhere. This afterglow marks a true horizon for sight. We cannot see through the earlier, opaque era because the light from that time could not travel. The name for the moment when the fog lifted is recombination, simply the time when free charges combined into neutral atoms. Past that, our view is blocked, not by a curtain someone could pull back, but by the way matter and light behaved in that young, hot ocean. And yet, this horizon is not frozen. Every second that passes, a new second of ancient light arrives. In that very narrow sense, our observable bubble grows by about 1 light second each second. But remember the stretching of space. While we receive new light, the places that sent it keep drifting farther away. The map of what we see and the map of where those sources are today do not match. We always see where they were, not where they currently sit. Because the cosmic microwave background comes from everywhere, it lets us take the universe's temperature across the whole sky. What we find is a smoothness that is almost shocking. The temperature changes by only a few millionths of a degree from place to place. Those tiny ripples matter. They are the faint fingerprints of the first small clumps of matter, the seeds from which galaxies, stars, and eventually planets would grow. Picture a pond so flat you can barely see the rings from a pebble. Those slight rings are enough to guide how the water moves. In the same way, the small temperature differences guided gravity, and gravity slowly gathered matter into the structures we now see. On the very largest scales, the universe appears homogeneous, a word that simply means the same in every big enough sample. Think of a well-mixed cake batter. Scoop here, scoop there, and you get roughly the same mix of ingredients. Our maps of the microwave afterglow hint at this sameness. If our observable bubble contains on the order of trillions of galaxies, then a similar bubble centered far away should hold a similar number. Not because the two regions know about each other, but because the rules and starting conditions were alike, and the unevenness was tiny. It is a quiet kind of order, not neat like a grid, but balanced on average. This idea has a curious consequence when you let your mind step beyond our horizon. If space is truly endless and stays roughly the same in its broad strokes, then any arrangement of matter that can happen in a region of a given size will happen somewhere, and not just once. There are only so many ways to arrange a finite set of particles within a finite volume. Given endless room to try, those arrangements repeat. This is not a mystical claim. It is a simple statement about combinations and size. If you shuffle a deck of cards long enough, you will eventually see the same order again. The universe is not a deck, and atoms are more complex than cards, but the logic is alike. In an infinite, homogeneous space, patterns recur. What does that mean for us? It suggests there may be regions so remote that their light will never reach us, where matter has fallen into shapes much like the ones here. Somewhere, in a place forever out of reach, there could be a galaxy like the Milky Way, a star like the Sun, a planet with seas and wind, and a person reading these words. There could also be places where the stories split in small ways, a different path taken, a different cloud of gas forming a star earlier or later, a different branch on the tree of life. This is a working picture drawn from mathematics and from the large-scale sameness we observe. It is not proof of doubles you could meet. It is a calm acknowledgement of what infinity does to possibilities. If that thought feels too large, bring it back to the scale of breath. Our true neighborhood is modest. A star, some planets, a few bright companions in the nearby sky. The horizon we live within does not lessen the value of what we can touch and know. It simply frames our place in a wider map. The microwave glow that surrounds us is a gentle reminder that the universe has a memory and that light carries it with care. The fog analogy reminds us that not seeing is not the same as not existing. The deck of cards idea reminds us that chance and repetition can build patterns across space the way rhythms build music across time. Notice, too, how the different pieces fit together without force. The speed of light sets how quickly messages travel. The age of the universe sets how long they have had to move. The expansion of space stretches both the paths and the signals. Together, they draw a round window, our observable universe, with a radius of about 46 billion light-years. Within that window, we read the afterglow from 380,000 years after the beginning, and the red-shifted light from galaxies across cosmic time. Beyond it, the meadow continues in the mist, likely with the same broad character we see here. We do not need to rush the unknown. The sky keeps arriving, second by second, photon by photon, and each arrival is another page of the same quiet story. There is a gentle comfort in this limit. A horizon gives shape to experience. It encourages patience. When we accept that some parts of the universe are not yet visible and may never be, we can lean more fully into what is here. The way light changes color as it travels, the way tiny temperature ripples grow into galaxies, the way space expands without needing an outside room. If the universe is wider than any map can hold, then our task is simple and kind. Listen to the light we have, learn what it tells us, and let the rest remain as soft possibility. Like the edge of a foggy field before sunrise, one quiet consequence of that wider map is the idea of repetition at impossible distances, where the math suggests there are copies of our arrangements, of galaxies, of towns, even of choices so far away that the number describing their distance is written as 10 to the power of 10 to the power of 115 meters, a stack of exponents so large that the digits would spill past the edge of anything we could draw. And yet, if space truly has no end, even such distances are still just distances, finite steps along an endless road, which means somewhere in that far country another version of you might be easing into the same thought, smiling at the strangeness, while another version even farther away does the same. This picture rests on a simple assumption that the universe beyond our horizon resembles the part we can see, and most days that seems reasonable. Though recent surveys whisper that our local neighborhood might be a little unusual, a cosmic lowland with fewer galaxies than average. a gentle void where things are spread thinner than they are elsewhere. So, if we could look beyond our observable edge, we might find busier regions where galaxies crowd closer and black holes are more common and the sky would bloom with activity. Or we might find stretches that are almost empty, like deserts between oases. Some theories take that variety much further and suggest that in the universe's first moment, during a burst of growth called inflation, a tiny fraction of a second, when space itself swelled at a near unthinkable rate, different patches could have settled into different patterns, with different physical settings, as if the knobs that set the behavior of particles and forces were tuned to other values. This could give rise to pocket universes with rules that do not match ours, places where our textbooks would read like poetry rather than instruction. And while that is still speculation, it gently reminds us that our familiar corner may not be the whole menu of what reality can serve. Under all that wonder sits a quieter question that changes the shape of our thinking. What if the universe is not infinite at all? And even if it is infinite, what does it mean to say that an expanding infinity gets bigger, when in math, adding to infinity still leaves infinity? Multiplying infinity by 2 still leaves infinity? So how can growth make sense here? The answer is to notice that expansion does not add new amounts of infinity. It changes the scale, the ruler itself, so that every distance becomes larger, while the overall character remains. Like an endless sheet of graph paper where each square is 1 inch across, and then the sheet is stretched, so each square is 2 inches across. Still endless, still with infinitely many squares, only now every pair of marked points is twice as far apart. That is what cosmologists mean when they speak of expansion. Not a universe becoming more infinite, but one where the yardstick grows. So a galaxy that is 100 million light-years away today could have been 50 million light-years away when the universe was half its current size. From this, a quieter but profound picture follows. If the universe has no end today, it had no end at the beginning either, meaning the Big Bang was not a fireball exploding from a single point into empty surroundings, but an everywhere event, the whole of space beginning to expand and cool at once. Every point can fairly say it sits at the center of what it sees, because from every point the pattern of expansion looks the same, and that helps explain why the sky is so even on large scales, and why no edge or center shows up in our maps. Still, if space holds unlimited matter and energy, why does it not crush itself under infinite density? The answer is in the idea of density itself. How much stuff per volume? So even if both the stuff and the room are limitless, their ratio can settle to a gentle average, on the order of a few hydrogen atoms in each cubic meter, a thinness that leaves the big picture calm. The personal twist of an endless, even universe is that every possible arrangement of matter in a region like ours should happen somewhere, not once, but over and over. So the idea of distant doubles is not a mystical mirror, but the plain outcome of combinations repeating across unending room. And if that feels too heavy, remember that a deck of cards shuffled long enough will yield the same order again, not because the deck has a memory, but because possibility returns in a big enough space of tries. Choosing a universe with an edge does not avoid the tangle either, because a finite cosmos invites its own hard questions about what lies beyond any boundary, whether outside can mean anything for space itself, and what a traveler would meet at an end to distance. This is one reason many scientists favor models that are either truly endless or so vast that any bend is too slight to measure, a view supported by the smoothness of the cosmic microwave background, whose gentle temperature map suggests that space is very close to flat and could stretch without limit. In that reading, the growth we witness is not like adding rooms to a house, but like stretching the fabric of a sweater so every stitch moves away from every other stitch in a steady, even way. That leads naturally to the next puzzle. What drives this steady stretch? What keeps the sweater easing outward where no hand is pulling? Here we step into the soft hum of the quantum vacuum, a name that can mislead because it sounds like nothing at all. Yet the quantum vacuum is an active nothing, a restless background where tiny pairs of particles flicker in and out of existence too quickly to last. Like brief ripples that cancel almost as soon as they form. This process, called quantum fluctuation, leaves even the emptiest space with a small but real energy. You can think of it as a faint pressure that belongs to space itself. And unlike the gravity from matter, which pulls things together, this vacuum energy acts as a kind of negative pressure, a push that urges space to expand. So the more space there is, the more of this energy you have, and the more of this energy, the stronger the gentle push becomes. A feedback that helps explain why expansion not only continues, but seems to speed up on the largest scales. When we say new space appears, we do not mean that bricks of room are delivered from somewhere else, but that distances increase everywhere at once. And within our observable bubble, the added volume each second is staggering, on the order of 10 to the 78th cubic meters. So large that counting to that number 1 per second would take longer than the universe has existed by, a factor beyond easy grasp. Yet, this is not a factory filling shelves. It is the quiet default of the vacuum's energy at work. None of this cancels the warmth of the familiar world, where atoms hold hands and gravity gathers stars, and local bonds are far stronger than the slow cosmic push. It only sets those comforts inside a larger rhythm, one where an infinite sheet can stretch without edges, where a beginning can happen everywhere at once, where density can be thin and steady though the total is unbounded, and where the deepest emptiness is not empty at all but softly alive with the energy that keeps the great distances growing. As space stretches, it makes room for more of the energy that belongs to empty space itself. That extra room feeds the process, and the process feeds on the room. In the first instant of the cosmos, this feedback became a runaway called inflation. Nothing outran light through space. Rather, space grew so quickly that light could not keep up with the new distances opening between points. Imagine trying to cross a treadmill that speeds up faster than you can run. The belt slips beneath your feet faster than your steps can land. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton ballooned to about the size of a basketball. It sounds like a fable, yet it falls out of the rules of the very small. Quantum mechanics allows tiny borrows of energy for very short times, the uncertainty principle, so long as the books balance quickly. During inflation, the universe borrowed a huge amount of energy from the vacuum to make new space, then used the expansion itself to settle the debt. It is a little like taking a loan to buy a money printing machine, then using the new bills to pay the loan back, only the machine worked so well it overdid it. Inflation didn't stop at just enough to tidy the early cosmos. It overshot, generating far more room than the minimum. Our entire observable bubble is only a pin-sized patch on a balloon blown up to the size of Earth. That is the scale of the story. A pinhead of view on an Earth-sized spread of space. Stranger still, the growth did not simply end. What we see today is not inflation itself, but a slower cousin that runs on similar ideas. A form of energy, dark energy, seems to fill space evenly, making up about 2/3 of the total content of the universe. It acts like vacuum energy, with a gentle push that accelerates the expansion. As space grows, there is more room for dark energy, and the soft push continues. At first glance, this looks like a crime against the rule that energy cannot be created or destroyed. Where does the new dark energy come from? The resolution lives in gravity's ledger. Gravitational potential energy is counted as negative. As matter spreads out with expansion, the universe's gravitational binding weakens, which lowers that negative balance. The fall in negative energy can offset the rise in the positive energy of the vacuum. The total can stay in balance, even while distances keep growing and more empty room appears. In that sense, the universe can create endless new space without breaking its own accounting. The rhythm is slow but steady, moment by moment, more room, more dark energy, more gentle acceleration. Expansion does not need somewhere to go. It makes its own room by widening the scale we measure with. The tale may be bold, but the evidence is simple and close at hand. In the 1,960 seconds, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, set out to chase a stubborn hiss in their antenna. They aimed the horn at different parts of the sky, cleaned the hardware inside and out, even scraped away bird droppings, yet the noise would not leave. What they had found was not a flaw, but a fossil, the sky-wide glow of the early universe, cooled and stretched by billions of years of expansion. We call it the cosmic microwave background, the afterglow of the beginning. That discovery earned a Nobel Prize and gave us a direct, steady light from the young cosmos. Why is that glow so rich with meaning? Because the very stretch of space is written into its color. When that light first slipped free, the universe was as hot as a small star, around 3,000 degrees, and the glow was invisible light. As space expanded, the light's waves were pulled longer, first into infrared, then into microwave, and today even into radio, until the average temperature of the glow is only about 2.7 degrees above absolute zero. It whispers rather than burns. Yet across the sky, it is astonishingly smooth, uniform to within a few parts in 100,000. That smoothness is exactly what a brief blast of inflation would produce. By stretching space so quickly, inflation ironed out early lumps and wrinkles. The tiny irregularities that remain, those few in 100,000 ripples, carry an even deeper message. They are the fingerprints of quantum jitter, little random differences in the very early vacuum that inflation pulled from subatomic scales to cosmic scales. Those slight highs and lows in density became the seeds that gravity later gathered into galaxies, stars, and the worlds around them. Your body, your home, your night sky all trace back to those faint, ancient ripples. Later satellites, like Kobe and Planck, mapped these temperature speckles across the whole sky with exquisite detail. The patterns match what inflation predicts so closely that we can read core facts right out of the glow. Space is flat to the limits of our measuring sticks. Ordinary matter, the stuff of atoms, makes up only about 5% of the total. The expansion rate and age of the universe can be pinned down with high accuracy. All of this, teased from a sky-wide static that once looked like nothing more than noise. The afterglow also gives us a new way to picture our beginnings. It shows that everything we can observe today, every galaxy we can ever hope to image, once fit into a region about the size of a beach ball. That does not mean a tiny ball sitting in a larger room. The ball was the room. Space itself was that compact region of spacetime, and there was no outside to hold it. As expansion began, the ball did not push into anything. The distances within it simply grew. This is hard to picture because daily life trains us to imagine shells and containers. The early universe asks us to relax that habit. The container and the contained were the same thing. If all that space was once so compressed, what powered the grand widening? The trail loops back to the quiet force we have already met. Dark energy, invisible and smooth, makes up most of the energy content of the universe, yet it leaves no direct mark on our eyes. How did we come to notice a thing that hides so well? By watching how the universe's speed has changed with time. For most of the 20th century, astronomers expected gravity to act as a brake. With enough mass pulling on itself, expansion should slow, maybe even stop or reverse. In the late 1,990 seconds, two teams set out to measure that slowdown by studying special supernovas, stellar explosions bright enough to serve as standard candles across vast distances. The plan was straightforward. Compare how bright these supernovas looked with how much their light was redshifted, and from that, chart the history of the expansion's pace. What they found was the opposite of what they went looking for. Instead of a strong brake, the data showed a soft foot on the gas. Distant supernovas were dimmer than a slowing universe would allow, which meant they were farther away than expected. They had been carried off by an expansion that had sped up. The result was clear enough and startling enough to change the story of the cosmos. The universe is not just growing, it is accelerating in its growth, as if the fabric has a built-in springiness that encourages more space to appear over time. That springiness is what we call dark energy. It does not clump or glow, it does not make stars or dust, it just lives in the emptiness, and by living there it pushes the emptiness to be roomier still. The picture that emerges is patient and consistent. Inflation in the first breath smoothed and enlarged the young universe far beyond what a slower start could do, blowing up quantum flecks into the seeds of structure. The afterglow preserves a snapshot of that time, its color and pattern agreeing with the theory's quiet claims. The present-day expansion, driven by dark energy, keeps the distances growing and even speeds them up, not by breaking the rules, but by following the book of gravity to the letter, with negative gravitational energy balancing the positive energy of the vacuum. Energy is not conjured from nowhere. The ledger stays even while the ruler stretches. If the numbers feel large enough to float out of reach, bring them back to the images. A treadmill you cannot outrun, a proton's speck swelling to a ball in a blink beyond measure, a beach ball that was not inside the universe but was the universe, with no outside to speak of, a sky-wide hiss that turned out to be a baby picture, its faint freckles the plan for everything that would come. Supernovas like mile markers along a highway, showing that the car did not slow as expected, but picked up speed. Each image is a gentle handhold. Together they tell a simple story told on a grand scale. Space expands by changing its scale, not by finding a bigger room. The early universe grew in a rush that set the stage. The present universe grows with a whisper that will likely never end. Within that whisper, the everyday world remains steady. Atoms keep their bonds, stars keep their orbits, galaxies hold together where gravity is strong. The cosmic push is slow and delicate up close, only winning across great spans where nothing else holds fast. That is why your table does not stretch, why the moon does not drift away, why the Milky Way will still meet Andromeda in a far-off future. The grand widening is a background tempo, not a local storm. It is the rhythm by which room is made for more time, more light, more quiet. Even so, the questions it raises are generous. What exactly is dark energy? Why does the vacuum have the amount of push it does, and not more or less? Did inflation happen once everywhere? Or does the engine that started our patch run on in other places beyond our view? The night offers no quick answers, only the steady arrival of new light and the patient work of listening. For now, we welcome the story the sky has already told. A beginning that was everywhere at once, a middle that is still widening, and a future where the ruler keeps stretching while the ledger stays balanced. Type Ia supernovas are a special kind of stellar explosion that reach nearly the same peak brightness each time. That steadiness turns them into reliable lighthouses across the dark. By comparing how bright they look with how bright they should be, astronomers can measure precise distances to their host galaxies. Then they match those distances to redshift the stretching of light as space expands. The plot should have traced a gentle slowdown under gravity's pull. Instead, it bent the other way. The most distant supernovas looked too dim, meaning too far, meaning space had grown more than expected while their light was en route. The calm reading of that surprise was simple and stunning. Expansion is accelerating. Something gives space a steady push that becomes more important over time. We call that something dark energy. It doesn't glow, clump, or form stars, yet it dominates the cosmic ledger. By our best accounting, it is about 68% of everything, outweighing ordinary matter by more than 13-1, and even outmuscling dark matter, the unseen scaffold that holds galaxies together. For all that influence, we still do not know what it truly is. Dark energy behaves in a way that goes against everyday intuition. Take the same amount of matter and spread it into twice the volume. The density halves. Dark energy's density, by contrast, stays about the same as space grows, so its total effect rises with the volume. In the early universe, hot, crowded, and bright matter and radiation ran the show. Gravity tugged on everything, slowing the expansion. As space widened and matter thinned out, the steady push of dark energy came forward. About 5 billion years ago, roughly when our solar system was taking shape, dark energy took the lead. The cosmic slowdown turned into a speed-up. Day by day it is too subtle to notice, but across long spans the change is dramatic. In the far future, many galaxies will be carried away so quickly by the expanding fabric that their light will never reach us again. They do not outrun light through space. Rather, more space appears between us than light can cross. What is this quiet engine? A leading idea is vacuum energy, the energy of empty space itself, rooted in quantum fields that never fully rest. Even the cleanest vacuum seethes with tiny pairs of particles flickering in and out of existence. When we try to calculate how much energy that sea should hold, the result is wildly too big, off by about 10 to the power of 120, compared with what the sky shows. It is the most famous mismatch in physics. Either we are double counting in a way we do not yet understand, or there is a hidden mechanism that cancels almost everything, leaving just a thin residue that drives acceleration. Other options remain open. Dark energy could be a new, smooth field pervading space, changing only slowly with time. Or gravity itself could act a little differently on the largest scales than it does nearby, so our equations might need a gentle correction at long distances. For now, we hold the measurements closely and keep listening. To appreciate how a push like this can shape the whole story, it helps to look back to the first instant. There was a brief period when expansion itself was faster than light could cross the growing gap between points. No rule was broken, nothing moved through space faster than light, but space widened so quickly that light could not keep up. Imagine two ants on a rubber balloon that starts to inflate faster and faster. No matter how they hurry, the rubber between them stretches faster than they can crawl. That early rush is called cosmic inflation. In an instant so short we write it as 10 to the minus 35 seconds, the size of the universe leaped by a factor written as a 1 with at least 26 zeros. Light, which travels about a foot in a billionth of a second, could not cross even the width of a proton during that burst. The energy for this came from a field we call the inflaton, a hypothetical quantum field that filled space and got stuck in a false vacuum, a high-energy state that acts like supercharged dark energy. While it was stuck, exponential growth took over. Double, then double again, over and over, everywhere at once. Inflation smoothed and flattened the young universe. Early bumps and curves were stretched so much that, on the largest scales, the sky looks nearly the same in every direction and very close to flat, like a basketball blown so large that its surface appears flat to an ant. Just as important, inflation took the tiny quantum jitters present in any field and stretched them from subatomic sizes to cosmic ones. Those small highs and lows in density became gentle hills and valleys across space. Gravity later pulled more matter into the hills, leaving the valleys thinner. Over billions of years, those seeds grew into galaxies, clusters, stars, and worlds. The idea carries a sobering footnote. If a field can drive such a burst once, perhaps patches of space can drop into a similar state again, in other times and places. A new bubble of inflation would expand at light speed, changing the local rules inside. Because it would arrive at light speed, there would be no warning. Physicists add an important calm. The chance of such an event happening in our patch appears extremely small. It is a reminder of deep uncertainty, not a daily fear. Once you accept that inflation can start in one region, it is natural to consider others. Quantum fluctuations could trigger more bursts elsewhere, again and again, creating many bubble universes within a larger whole, a multiverse. Each bubble expands and cools on its own, perhaps forming galaxies and stars under its own set of constants. While you read this, other bubbles could be growing in regions forever beyond our reach. This is not a tale chosen for drama. It is a straightforward extension of the same math that fits our sky. Each bubble might follow slightly different rules. Gravity could be a bit stronger in one, a bit weaker in another. The mass of the electron could shift. Even the number of large spatial dimensions might differ. Most such worlds would be barren, either too lumpy and quick to collapse, or too loose for matter to gather. Our patch would then be one of the rare places where the settings allow chemistry, complexity, and life to take root. Back in the part we can measure, the evidence lines up. Type Ia supernovas mapped the turn from slowing to speeding up. The cosmic microwave background, the faint afterglow from when the universe first became transparent, shows a sky that is amazingly smooth, just as inflation would predict, with tiny temperature ripples matching the pattern expected if quantum fluctuations were stretched to grand size. From those ripples we read off numbers with care. Space is flat to the limits of our measurements. Ordinary matter is only a small share of the total, and the age and expansion rate of the universe can be pinned down with striking precision. Dark energy's behavior remains the puzzle at the center. Because its density stays roughly constant while space grows, its total influence increases with time. That is why it was small in the past and large now, and why simple models of the far future look lonely. Galaxies not held to us by gravity will slip beyond view. Our local group, the Milky Way, Andromeda, and their companions will stay bound, even as the wider web grows thin. None of this means our everyday world will drift apart. Local forces still lead nearby. Atoms hold their bonds. Planets keep their paths. Galaxies hold together where gravity is strong. The cosmic push is a background tempo, winning only across great spans where nothing else ties things down. That is why your table does not stretch, why the moon does not drift away from Earth, and why the Milky Way will still meet Andromeda in a far-off future. The open questions are generous and steady. What sets the value of the vacuum's push? Is dark energy truly constant, or does it change with time? Did inflation happen only once in our past, or is the engine still running in distant regions, budding new universes forever? Could gravity be subtly different than Einstein's picture at the widest scales, hiding that difference in ways only the largest maps can reveal? Each question invites better measurements, new ideas, and patience. It helps to keep the pictures close at hand. Lighthouses in the form of supernovas, all shining with almost the same peak light, a plot that bends the wrong way, revealing a universe that picked up speed, a sky-wide hiss that turned out to be a baby picture, smooth, faint, and full of meaning. Its freckles the plan for everything to come, a balloon blown so large that its curve looks flat, ants that can never meet because the rubber between them swells too quickly, a treadmill that accelerates faster than your feet can run. Each image is simple enough to hold in a quiet room at night, yet deep enough to carry the weight of the mathematics behind it. In this picture, the universe does not expand by pushing into and outside. It grows by changing its own scale, making more room within itself. The early rush set the stage. The present whisper carries it forward. We stand inside our observable bubble, reading the light that arrives and tracing its stories backward. We hold the pull of the familiar and the push of the unknown, and we let both sit together, easy as breath, while the distances widen and the night keeps its patient glow. Most possible universes would be quiet and empty. Some would never form atoms at all because the basic forces are wrong for chemistry. Others would swell forever in a state of non-stop inflation, always too hot and too wild for stars to take shape. Yet if the larger reality is truly endless and keeps trying new settings, even the rarest recipe will appear somewhere. However unlikely our mix of constants may be, an infinite number of tries means there are endless chances to land on a set that allows life to spark. We find ourselves in a habitable bubble not because we were chosen, but because only in such bubbles can anyone wake up, look around, and ask these questions. This simple idea is called the anthropic principle. It does not say the universe was made for us. It says we naturally show up in the small set of places where life can grow, the way fish are found in water and not on dry rock. Fine-tuning may look uncanny from the inside, but in a big enough reality, unlikely does not mean impossible. It just means rare. Still, the multiverse carries heavy thoughts on its back. If there are infinitely many universes, and each tries out different histories, then every could have been happens somewhere. Every road you did not take is taken by another version of you in some far bubble. A joy you never found is found by another you. A hardship you escaped finds a different you. With infinite copies, uniqueness seems to fade, and choice can feel thin. If everything happens, do our decisions matter? Here is a softer way to hold it. Even if far-off versions of events play out elsewhere, your thread is still yours. The meaning of your choice lives in this path, with these people, in this moment. Those other worlds, if they exist, are beyond reach and influence. They do not dull the weight of kindness here, or the cost of harm here. Physics can widen the stage. It does not erase the reality of the scene you're in. Another worry is scientific. By definition, bubbles beyond our cosmic horizon cannot send us light or tug us by gravity. We cannot point a telescope at them, measure them, or test their details. Some scientists argue that a theory that cannot, even in principle, be tested rises to philosophy rather than science. That pushback matters. But note the path that brings us here. The same math that explains our early universe. The math of inflation often leads to eternal inflation and bubble formation as a natural consequence. We do not claim to see the other bubbles. We notice that the equations which fit our sky tend to make them, and our sky does offer checks. The cosmic microwave background carries subtle patterns that match inflation's predictions remarkably well. Those matches strengthen our confidence in inflation and, indirectly, keep the door open to a larger multiverse beyond what we can test today. Even that picture may be small compared to what some theories suggest. What if space has more directions than we can sense? Our daily world has 3, left, right, forward, back, up, down. But some attempts to tie all of physics together, such as string theory, work best when space has 9 directions in total, with 6 curled up so tightly that we never notice them. Think of an ant walking along a garden hose. From the ant's view, the hose is a one-dimensional line. You can go forward or back, but the hose also has a tiny circle around it. The ant could, in principle, go around the hose too, though that loop is small compared to its stride. In the same way, our space might hide extra directions wrapped so tightly that even particles cannot explore them. If those hidden directions are real, they could change how we think about expansion. Our familiar 3-dimensional space might be a kind of sheet, a brain, short for membrane, floating in a higher dimensional bulk. Most particles and forces would be tied to the brain, like beads glued to a sheet, while gravity could leak into the bulk. That leaking could explain why gravity feels so weak compared to the other forces. It is not weaker in itself. It is just spread thin across extra directions. In this view, the expansion we measure is our brain stretching within a larger space we cannot step into. Now tilt the picture a little further. If our brain exists, other brains might exist as well, stacked nearby along those hidden directions. They could be so close that the gap between brains is less than a millimeter, yet the direction of that gap is one we cannot point toward. Another version of you could be reading these words on a sibling brain, a whisper away in a dimension you cannot move through. In some models, brains can drift and occasionally collide. A collision between brains would pour energy into our brain, lighting it up as a fireball. From inside, we might experience that event as a Big Bang. The smooth afterglow we see the microwave background could be the fading heat of such a collision, with inflation as the opening rush that followed. In a cyclical twist, brands might collide again after unfathomable spans, seeding new hot starts and fresh rounds of structure. The mathematics also allows stranger rhythms. Perhaps it is not our three directions that grow while we watch, but the hidden ones, while our local space stays almost the same. From our seats on the brain, we would still read the signs as expansion because the geometry we can measure would change in the same way. Or perhaps some directions expand while others contract, leaving the total volume of space constant. Picture a balloon whose interior grows while its surface stays fixed. Living on the surface, you would not see the interior swell, only indirect effects. These ideas are bold, and they are still unproven. We try to test them at the limits of what our tools allow. The Large Hadron Collider smashes particles together at tremendous energies and watches for missing energy products that would suggest a particle slipped off our brain into a hidden dimension. So far, no clear sign has appeared. That does not end the story. It may mean the extra directions, if they exist, are curled tighter than we can reach, or that the energies needed are far beyond what we can build. The math that points toward extra dimensions remains compelling to many researchers because it knits together pieces of physics that otherwise sit awkwardly side by side. If extra dimensions do exist, they offer one clean answer to the old question: what is space expanding into? It may be expanding into directions we cannot perceive. Our three-dimensional world might be stretching like the skin of a balloon through a room we can never enter. But even if there are no hidden directions, our familiar space can still hold surprises in its shape. A space can be finite yet have no edge, the way the surface of a sphere is finite but has no border. It can also be wrapped, so that traveling far in one direction might, in theory, bring you back from the other side, like a game world with a looping map. On very large scales, our measurements so far point to a space that is close to flat and either very large or endless. Yet the possibility of unusual global shapes remains, waiting for sharper maps and quieter instruments. Where does that leave us tonight? In a good place, open, curious, and grounded. The multiverse may be vast, or it may be a mirage of math we have not fully understood. Extra dimensions may cradle our world, or they may belong to a different story. What we do have is light, ancient, patient, and generous, and the tools to listen to it better each decade. As we do, our pictures of reality grow more precise. Some speculations will fade, others will earn their place. Through it all, our small bubble keeps drifting outward on a sea of space, and our questions drift with it, steady as breath, humble before the dark, and bright with the wish to know. If space can fold back on itself, the question, what is it expanding into, begins to lose its bite. Picture a donut. As the donut gets fatter, it does not need a larger kitchen to grow into. It simply becomes a bigger donut. That sounds playful, yet it points to a serious idea. The shape of space sets what expansion means. In a flat, endless space, distances stretch without any special destination. In a curved, finite space, expansion can mean that a closed shape, one that wraps back on itself, simply grows in size. General relativity allows three broad kinds of spatial geometry. One is flat, like an infinite sheet of paper. Parallel lines stay parallel. The angles of a triangle add to exactly 180 degrees. This is the geometry most of us imagine by default. Another is positively curved, like the surface of a sphere. There, parallel paths eventually meet, and triangle angles add to more than 180 degrees. In such a closed space, you could set off in what feels like a straight line, and someday return to where you began. The third is negatively curved, like a saddle. Parallels drift apart, and triangle angles add to less than 180 degrees. That kind of space stretches forever with a gentle, open bend. Measurements of the cosmic microwave background and the large-scale arrangement of galaxies suggest our space is either flat or so close to flat that any curve is too slight to detect so far. But flat does not have to mean infinite. A sheet of paper is flat, yet you can roll it into a cylinder or glue its edges to make a torus, the donut. Locally, a small ant walking on the surface still experiences flat rules, but globally, the space is finite and wraps around. If the universe works like that, asking what it expands into becomes unnecessary. A donut that grows does not invade a larger outside. It just has more surface area than before. A wrapped space would leave clues. Light could circle the cosmos and return from behind you, making multiple images of the same distant object appear in different parts of the sky. The afterglow of the Big Bang might show repeating patterns, like matching rings, where light took different long paths around a looped universe. Astronomers have searched for these signatures and, so far, have not found them. That leaves two simple options. Either our space does not wrap at the scales we can see, or it does, but the donut is so large that light has not completed a lap, even once, since the beginning. The kitchen could still hold a donut just one wider than our current view. The shape question grows richer when you fold time into the picture. Space and time weave together into a single fabric spacetime, so any stretch in space touches time as well. In the early universe, when everything was close and hot, clocks would not have ticked the way they do here and now. As space expands, it carries time along with it, changing how distant events look and how we compare now in one place to now in another. This is where a famous puzzle becomes clear. Light has a speed limit, but space itself does not move. It simply grows. Distant galaxies can recede from us faster than light, without breaking any rule, because it is the space in between that is increasing. From a far galaxy's point of view, it is not flying through space. The fabric is stretching, and we are the ones drifting away. Because this is true at every location, every observer sees roughly the same pattern, themselves at the center of a web that is widening, with no special seat, no edge, and no preferred frame of rest. Expansion is the universe becoming more of itself, not entering somewhere else. Stretching space stretches time's story too. When you watch a far-off galaxy, you do not just see its light reddened, you also see its events slowed. A supernova that brightens and fades over a few weeks in a nearby galaxy can take much longer when seen in a galaxy with large redshift. The gap between the ticks of light is stretched by the same factor as the light's wavelength. Time itself, as read by your telescope, has been lengthened. For sources near the edge of what we can see, that factor can be around 10. To you, their clocks run 10 times slow. To them, looking back our way, the same would be true. Neither view is wrong. Each is shaped by the path light takes through an expanding space-time. This leads to a subtle lesson. There is no single, universal now that spans the entire cosmos. In everyday life, simultaneity feels simple. Two events happen at the same time, or they do not. Over galactic distances, relativity and expansion bend that intuition. The order and spacing of events depend on how you move and on how the fabric has stretched along the light's route to you. That does not mean time is an illusion. It means time is part of the geometry, not a separate stage. Return for a moment to the closed, donut-like space. If we lived in such a wrapped cosmos, expansion would show up as the donut getting fatter. There would be no need for an outside to fill. The space would simply contain more room within its own looped structure. You could imagine, in principle, a beam of light setting off and winding all the way around to reach you from behind, perhaps even many times, leaving a faint lattice of echoes. The absence of those echoes so far suggests our loop, if it exists, is much larger than the patch we see, or that the universe's global shape is different from a clean torus. Either answer keeps the main point. Expansion is a property of the fabric, not a motion into a container. Because space and time are tied, expansion also reshapes how we think about age. We say the universe is about 13.8 billion years old, and that number comes from tracing the expansion back in a model that fits a mountain of data. But when we observe far-flung regions, their stories play out in slow motion on our screens. Stars form, burn, and die on timescales stretched by the redshift. The early universe can seem to rush, galaxies forming quickly, black holes growing fast because the density and conditions then were so different. Compressed space brought compressed time, in the sense that processes that take eons today unfolded on shorter cosmic clocks back then. At the same time, expansion blurs the very notion of a shared timeline across the skies. If two explosions happened at once, separated by billions of light years, different observers might disagree about that at once, depending on their motion and on the way space is stretched between them. That sounds like a trick, but it is just the geometry doing its quiet work. The math that handles this, Friedman, Lemaitre, Robertson, Walker models, if you like formal names, gives us a consistent way to define a cosmic time that ticks with the expansion, even as local measurements differ by viewpoint. You do not need the equations to feel the gist. Time is not a separate thread. It is woven into the same cloth that carries distance. The practical, human scale result is comforting. Nearby, where gravity binds and forces are strong, clocks compare well and the world behaves as you expect. Your watch keeps time. A lab across town keeps the same time to a beautiful approximation. Across the deeps, the stretching shows itself as softened colors and slowed rhythms. The universe ages together in the large, yet each sightline carries its own gentle delay. So where does that leave the original question? If space is flat and endless, expansion is the ruler stretching everywhere at once, with no destination. If space is curved and finite, expansion is the closed shape growing, like the donut thickening, still without an outside to enter. If space wraps on itself in clever ways, our view may someday catch its echoes. If it does not, the absence will tell us our loop is larger than we can see, or that the global shape is of another kind. And throughout, time rides along with space, lengthening the beats we observe from afar and reminding us that now is local, stitched to our place and motion. None of this needs grand drama to be profound. You can hold it lightly. The sky above is a patient teacher. It shows us triangles in starlight and parallels in galaxy maps. It lets us measure curves and find so far almost none. It carries us baby pictures in a faint microwave glow and shows us distant fireworks slowed by the stretch of time. It invites us to accept that the universe expands by deepening its own geometry, and that your life, right here, moves within that quiet widening steady as breath, stitched to the same fabric, and part of the same long unfolding. The idea of a single, universal now does not survive at cosmic scale. What looks simultaneous to you will not line up in time for an observer in a distant galaxy. Each place slices space-time differently, so the present is local, not global. As expansion speeds up under dark energy's steady push, these time effects grow stronger. The stretching of space also stretches the way we experience time across great distances, like a slow tide, lengthening every interval between faraway beats of light. Watch a distant galaxy through a telescope, and you don't just see redder light, you see slower stories. A supernova that seems to brighten and fade over weeks nearby can take far longer when it plays out in a rapidly receding galaxy. The light's color is stretched, and so are the gaps between its pulses. Time, as you measure it from here, has been drawn out, pushed to the edge of what we can observe, and the factor can be around 10 events appear to run 10 times slower than they do in our neighborhood. As acceleration continues, future observers will see more extreme slowing still, until distant change looks almost frozen. Follow that thread far enough and a stark picture forms. Expansion keeps thinning matter and evening out temperatures. Energy gradients, the differences that power stars, chemistry, and life, fade. This long slide toward uniformity is called heat death, a state close to absolute zero where nothing useful can be done because there are no differences left to drive any process. It isn't a sudden wall, it's a slow settling as the universe spreads its contents so thin that activity dwindles everywhere at once. The rough timeline is immense. After about 100 billion years, the last ordinary stars will run out of fuel and wink out. No new stars will gather because gas will be too spread out for gravity to squeeze it into shining spheres. The cosmos will drift into the degenerate era, ruled by leftovers, white dwarfs, neutron stars, and cold embers that once were suns. Then the floor drops another step. Around 10 to the power of 34 years, written as a 1 with 34 zeros, protons themselves are expected to decay in many theories of particle physics. If that happens, atoms will not be permanent. The matter that built planets and people will slowly crumble into lighter particles. Electrons, positrons, and photons will trickle through the expanding dark, with fewer and fewer places to go. To grasp the scale, if you squeezed the current age of the universe into a single second, the proton decay era would last longer than 1 billion years in that same clock. After that comes the reign of black holes. They do not last forever. By a process called Hawking radiation, they slowly lose mass, giving off faint particles and energy. A black hole born from a large star needs far longer than today's universe has existed to evaporate entirely. The giants in galactic centers will take about 10 to the power of 100 years, one followed by 100 zeros. When the last of them sighs away, there will be nothing left to rearrange. No temperature differences, no chemical reactions, no computations, no life. Entropy, the measure of disorder, will be at its maximum, and the universe will settle into quiet equilibrium. This fate depends on dark energy continuing to act as it does now. If it stays steady, acceleration carries us along that path. Even before then, expansion shapes what anyone can learn. As the fabric stretches faster, more galaxies drift beyond our observable horizon. They are not destroyed. Their light simply can't ever reach us again. They fade and then vanish from our sky. Project forward some 150 billion years, and only our local group, perhaps a few dozen galaxies bound together by gravity, will remain visible. Future astronomers in the Milky Way will see a small, island universe surrounded by darkness. They won't witness galaxies rushing away, because the rush will lie beyond their reach. The best clue we have today, the cosmic microwave background, will also slip away. Expansion will stretch that ancient afterglow to such long wavelengths that it dissolves into undetectable hush. Those future scientists may conclude they live in a quiet, static cosmos, with no sign of a beginning and no map of a larger whole. There is a more dramatic branch on the tree of possibilities. If dark energy grows stronger with time, if its push increases, instead of staying constant, expansion could run away into what's sometimes called a big rip. Gravity would be overcome first, galaxy clusters would unbind, then galaxies themselves would be pulled apart. Later, solar systems would fail, then molecules, then atoms. Even the strong nuclear force, which binds protons and neutrons, could be beaten on the final approach. This is a speculative path, not the default one, but it shows how sensitive our future is to the vacuum's quiet push. That brings us to the last question in this chain. What is in the empty that gives rise to such effects? Empty space isn't empty. At very small scales, it is busy. Quantum theory says every field, like the field that gives rise to electrons or to light, keeps a residue of activity even in its lowest energy state. Tiny particle-antiparticle pairs wink into existence and then vanish, too quickly to see directly, yet with effects we can measure. This restless background is sometimes called quantum foam. Shrink your imaginary microscope below the size of an atomic nucleus and then keep going, down to the Planck scale, about 10 to the power of negative 35 meters. At that depth, the smooth idea of space-time begins to fail. Geometry itself is expected to jitter. Virtual particles borrow energy from the vacuum and return it quickly, a trade allowed by the uncertainty principle. The more energy borrowed, the faster it must be paid back. Nothing breaks conservation of energy. The loans are brief and balanced. Electron-positron pairs can flash into being for around 10 to the power of negative 21 seconds before destroying each other. Heavier pairs appear for even briefer instants. The vacuum crackles with these flickers everywhere, all the time. Though fleeting, the foam leaves fingerprints. It nudges the energy levels of atoms. It changes how light and matter move through fields. And on the largest scales, the average energy of this restless nothing shows up in gravity's equations as a gentle pressure that can push space to expand. That is why dark energy is often linked to vacuum energy. The same emptiness that seethes with particles for a heartbeat may, in the average, carry the small, steady push that drives the cosmos wide. Gather the pieces, and the story holds together. There is no universal now. Time is local, stitched to place and motion. Expansion stretches both distance and the rhythms by which we read distant events. Over vast spans, dark energy's steady hand spreads matter thin and turns off the engines that run on difference. The horizon tightens around what we can see, and the deep evidence of our origins fades from view. In some paths, the push grows wild and tears structures apart. In others, it simply hums on, long enough for stars to die, atoms to fail, and black holes to whisper away. Beneath it all, the vacuum, quiet to our senses, boils with brief appearances that still manage to tilt the fate of everything. It is a sober tale, yet not a grim one. The universe is not rushing to an end on our time scale. It is unfolding with patience beyond measure. In the meantime, stars still burn, chemistry still sings, and the local bonds that hold our world together are strong. The night sky remains a gentle teacher. It shows the stretch of space in the soft reddening of distant light, the stretch of time in the slowed flicker of far supernovas, and the deep, lively quiet of the vacuum in the way the whole fabric keeps opening, steady as breath, into more of itself. The vacuum is not bare. By the rules of quantum field theory, every kind of particle you can name, electrons, photons, quarks, and many you cannot easily picture, flash in and out of existence for a breath and then are gone. All of this unfolds in what looks, to our eyes, like perfect emptiness. The proof shows up in careful labs. Place two clean metal plates very close together in a vacuum and something subtle happens. Long wavelength virtual particles cannot exist in the narrow gap, while the wider space outside still hosts them. That mismatch creates a tiny pressure that nudges the plates together. This is the Casimir effect. It is delicate, but measurable. In a quiet room with the right instruments, you can feel the push of nothing. This small push opens a big question. If virtual particles fill space with restless energy, all those flickers should add up to an energy density in the vacuum. When physicists try to total it, the number that falls out is monstrous, about 10 to the power of 120 times larger than the dark energy we infer from the sky. If the vacuum really carried that much energy, space would rip outward so quickly that galaxies could not form. The fact that galaxies did form, and that we are here to notice, means the raw calculation is wrong or incomplete. Either we are missing a deep piece of quantum mechanics, or some hidden mechanism cancels almost all of the vacuum's contribution, leaving only a thin residue. That left over could be the dark energy that now accelerates the universe's growth. A small, surviving whisper, driving a very large story. There are other paths as well. Perhaps the vacuum contains hidden fields that dilute or balance one another. Perhaps extra dimensions, if they exist, allow the vacuum's energy to leak away where we cannot see it. Perhaps empty is not empty in ways our current language cannot capture. These are not comfortable answers. they are open doors. Some ideas suggest space itself has parts. In loop quantum gravity, space is not smooth but granular, built from tiny units linked like a crystal lattice, so small that ordinary measurements glide over them. In string theory, space might be something that emerges from the relationships among vibrating strings in higher dimensions, rather than a stage that exists first. In both pictures, what seems like nothing is a structure with inner workings. If space has components, then expansion can be thought of as stretching those components, not creating new emptiness out of thin air. Space would not expand into nothing because space itself is the something that grows. From the texture of the vacuum, the mind jumps to the far horizon of fate. What if the same expansion that now hums along were to intensify without limit? One path sketched by the equations is a violent end called the Big Rip. In this scenario, dark energy does not stay steady, it strengthens over time. The fabric would then stretch faster and faster until it overwhelms every binding force. Heat death is a slow fading. The Big Rip is a sudden tearing. The imagined timeline is chilling and detailed. About 1 billion years before the final moment, dark energy would beat gravity on the largest scales. Galaxy clusters, the great cities of the cosmos, would fall apart. No bridge of gravity could hold them. Individual galaxies would drift into isolation, stranded in widening black. Roughly 200 million years before the end, the unbinding would reach into the galaxies themselves. Stars would be pulled free from their spirals and ellipses, scattered into the dark as the fabric stretched faster than gravity could call them back. The Milky Way would dissolve. Andromeda would come undone. The familiar patterns of the night would be unrecoverable memory. Half an hour before the last moment, the rip would arrive in neighborhoods like ours. The pull that keeps planets circling their stars would lose to the push of expansion. Earth would part from the Sunday. The moon would loosen from Earth. In worlds across the cosmos, every planet would discover itself alone, heated only by what it carries within, as its star receded beyond help. 90 seconds before the end, the scale would shrink from the celestial to the intimate. Molecules could not hold. The space between atoms would expand faster than the electromagnetic forces that keep their bonds. Atmospheres would unravel into thin mist. Oceans would not boil from heat. They would fail from separation, their cohesion pulled apart by the growth of the room between molecules. A trillionth of a second before the end, 10 to the power of -12 seconds, the strong nuclear force would lose. Atomic nuclei would fall to pieces. Protons and neutrons, once snug in their cores, would scatter. Matter would return to its simplest ingredients. At the final instant, some models say even the way we measure distance and time, the metric of spacetime, would blow up. If that happens, causality itself would fail. There would be no before and after to describe. The story would not simply end. The idea of a story would no longer apply. That cliff, though, depends on how dark energy behaves. If its push stays constant, the Big Rip does not happen. The universe coasts toward heat death instead, a very long, very quiet evening. Only if the push grows with time does the tearing become unavoidable. Our best observations so far suggest dark energy has remained roughly steady, but the data still leaves room for slow changes. Better measurements of distant supernovas, of ripples in the cosmic background, of the way large structures grow, will narrow the possibilities. If the push is strengthening, we can even estimate dates. One careful set of assumptions places the Big Rip about 22 billion years from now. Bolder assumptions move it closer to the scale of a few billion years. Either way, this is not a calendar entry anyone needs to set. It is a map note on the far edge of what we can imagine. And even that edge may not be final. Some theories whisper that a tear in space-time could seed new beginnings as the energy released triggers fresh bursts of inflation and births new regions. A tragedy in one telling becomes a prelude in another. These are speculative ideas, patient roads for careful work. Step back from the futures and return to the way we know the present. The story of expansion did not start with equations. It started with light. How do you measure something as shy as the stretch of space itself? First you ask for distances across billions of light years. Then you ask for speeds that are not really speeds, receding rates caused by the fabric widening between places. The trick is to find steady beacons. Exploding stars give us those beacons. Some supernovas, type Ia, reach nearly the same peak brightness every time because of how they ignite. When a white dwarf star stealing matter from a companion crosses a sharp mass limit and runs away into fire. Because their peak light is predictable, their apparent dimness tells us how far away they are. Their spectra, the patterns in their light, tell us how much the universe has stretched since they shone. Match distance to stretch across many beacons, and you get a history of expansion written in the sky. At first glance, that seems almost too simple for such a grand question. In practice, it is exquisite work, calibrating nearby supernovas against even nearer, standard candles like Cepheid variable stars, correcting for dust that reddens and dims, comparing telescopes and surveys so that one set of measurements lines up with another. Layer by layer, the uncertainties shrink. When the farthest supernovas appeared dimmer than expected, the plot bent toward acceleration. The surprise held up as the data grew. Other checks followed maps of ripples in the early afterglow, patterns in how galaxies cluster that all point in the same direction. Under the quiet of these methods lies an elegant separation, motion through space, and the expansion of space itself. Both shift light toward the red, but not in the same way. By reading the full spectrum and by comparing objects across many distances, astronomers tease apart local motions from the global stretch. The result is not a single number, but a living curve, fast in the beginning, slowing as gravity gathered matter, and then, a few billion years ago, turning to a gentle speed up as dark energy took over. Everything we worry about in the far future and everything we hope to learn about the deep vacuum rides on reading that curve well. Whether the push stays constant or changes over time, whether the fabric coasts or rips, whether the vacuum's roar is mostly cancelled or cleverly hidden, all of it funnels through our best attempts to weigh light, measure distance, and watch how patterns grow. It is slow, careful work, done in the glow of dying stars and the hush between galaxies, and it keeps teaching us the same lesson in new ways. Space does not expand into anything else. It deepens its own geometry. The vacuum is not empty. It is quietly alive. And the universe we inhabit keeps widening by those rules, steady as breath, while we learn to listen better to what the light has been telling us all along. Type Ia supernovae happen when a white dwarf steals matter from a companion star until it crosses a sharp limit, then runs away into a thermonuclear blaze. Because the trigger is so similar each time, these explosions reach nearly the same peak brightness wherever they occur. That steadiness turns them into standard candles, reliable yardsticks across deep space. The method is simple in spirit. Measure how bright the blast looks to us, compare it with how bright we know it truly is, and the difference tells us the distance. Farther things look dimmer, nearer things look brighter. At the same time, we read the spectrum of the light to find its redshift, the amount its wavelengths were stretched while traveling through the expanding cosmos. A larger redshift means more stretch, which usually also means greater distance and an earlier moment in cosmic time. When astronomers plot many supernova distances against their redshifts, the graph becomes a history of expansion. If the universe's growth rate had stayed steady, the points would fall along a straight line. If gravity had slowly won for a while, tugging everything back, distant supernovae would look a bit brighter closer than the straight line predicts. Instead, the farthest ones look dimmer farther than the steady case. Their light crossed a universe that expanded more than expected on the way to us. The clean, repeated message is acceleration. Expansion has been speeding up for billions of years. Supernovas are not the only tools. To trust distances on the largest scales, astronomers build a cosmic distance ladder, each rung calibrated by the one below. The first rung is parallax, the tiny, yearly wiggle of nearby stars against the background as Earth orbits the Sunday. With the orbit's size as our baseline, the parallax angle yields precise distances out to hundreds and now thousands of light years, thanks to space missions. Those nearby stars let us calibrate the second rung. Cepheid variables. Cepheids brighten and dim with periods tied directly to their true power. Measure the period, and you know the intrinsic brightness. Compare it to how bright the star looks, and you have its distance. Cepheids can be measured in nearby galaxies, anchoring the next rung. Type Ia supernovas which push the ladder out to billions of light years. Because each step depends on the one below, the whole ladder is sensitive to quiet errors. That sensitivity sits at the heart of a major debate. The value of the Hubble constant, the number that sets the current expansion rate. Local, ladder-based methods tend to give a value around 73 kilometers per second per megaparsec. Read another way. For every 3.26 million light-years of distance, space adds about 73 kilometers per second to the recession speed. But when scientists infer the same number by fitting the cosmic microwave background, our baby picture of the universe, with a well-tested model, they get a lower answer, about 67 kilometers per second per megaparsec. The difference is only a few percent, yet it is stubborn and statistically strong. Either there are lingering systematics in one or more steps of the ladder, or the simple model we use to read the microwave sky is missing a piece of physics. The community calls this the Hubble tension. The story is still unfolding. Despite that tension, both approaches agree on the big shape of the tail. The universe is expanding, and that expansion is accelerating. To turn observations into a clean, shared language, cosmologists use a single function called the scale factor, written at. It is a calm idea with a lot of power. The scale factor tells you how distances change with time. If it doubles, every large distance doubles. If it triples, they triple. By convention, we set A equals 1 today. Earlier in history, A was less than 1. In the future, A will be greater than 1. This function ties redshift to time in a neat way. If you observe a galaxy with redshift Z, you are seeing it from a time when the scale factor was A equals 1 divided by 1 plus Z. So a galaxy at Z equals 1 appears as it was when A equals 0.5, meaning the universe was half its current size in each direction. The cosmic microwave background carries a redshift of about 1090, so it comes from a time when A was roughly 1 over 1091, about 1,000th of today's size. Shrink each dimension by 1,000, and the volume shrinks by 1,000 cubed, so the universe's volume was about 1 billion times smaller when that light set out. Once you frame things with it, you can talk about acceleration precisely. If A grows linearly with time, expansion would be steady. If A grows faster than linear, expansion accelerates. If it grows slower, expansion decelerates. Observations suggest that for the past 5 billion years, ET has been growing faster than linear. That matches the supernova evidence. The universe's expansion turned the corner from slowing to speeding up around the era our solar system was forming. With Einstein's field equations, the scale factor does more than describe, it predicts. The equations connect the way ET curves with time to what the universe contains. The rule of thumb is simple. The more energy density the universe has at a given moment, the more it affects the expansion rate. In the early universe, when matter and radiation were squeezed into a tiny volume, the energy density was enormous. Expansion started fast and then slowed as the universe grew and thinned out. Later, a new player, dark energy, rose to dominance and reversed the trend, creating the current acceleration. Different futures unfold, depending on how dark energy behaves. If dark energy is truly constant, 8, will grow exponentially, forever. Distances will keep increasing at an accelerating rate, but the acceleration will settle into a steady pattern. In that picture, matter spreads thinner with time, and the universe drifts toward heat death, a long, quiet evening with no gradients left to power change. If dark energy strengthens with time, will grow faster than exponential. That leads to the Big Rip, where the push eventually overwhelms all binding forces. If dark energy fades or turns negative, gravity could regain control. The expansion might slow, stop, and reverse in a big crunch. The data at hand favors the first option, a nearly constant dark energy driving continued acceleration. The scale factor also gives a clear map of what the universe is made of today. Fit the best A curve to many kinds of data supernovae, the microwave background, the way galaxies cluster, and a simple mixture fits well. About 68% dark energy, 27% dark matter, and 5% ordinary matter. As it grows, the densities of matter and radiation dilute, while dark energy's density appears to stay roughly constant. That means dark energy's share of the total keeps climbing. In the very long run, ET heads toward the exponential growth of a de Sitter-like state, where dark energy rules the ledger. These tidy statements rest on long chains of observation. Parallax gives us the baseline. Cepheids pull us into the nearby galaxies. Type Ia supernovas carry us deeper, each one a flare that says, "I am this bright. How far must I be to look this dim?" Their spectra show how much the light has been stretched by expansion. Put distance and redshift together for hundreds of cases, and the plot shows the turn to acceleration. Cross-check that plot against the ripples in the cosmic microwave background, the frozen sound waves from the young plasma, and against the preferred spacing of galaxy clusters, and the same emerges again and again. Along the way, the ladder is rebuilt and refined. Space telescopes recalibrate Cepheids. New supernova surveys correct for dust and selection effects. Independent distance markers like tip of the red giant branch stars or water mazes orbiting black holes offer fresh anchors. On the microwave side, better maps of tiny temperature and polarization patterns sharpen the model fits. Each improvement narrows the uncertainties on ET, the Hubble constant, and the mix of ingredients. Each also tests whether the standard picture needs a new piece. The scale factor framework does something else that is quietly profound. It shows that expansion is not about moving into an outside. It is about how the ruler we use to measure distance changes with time. When it doubles, the number of ruler marks between far galaxies doubles. There is no edge necessary, no surrounding room, only the same fabric taking on a different scale. That is why redshift is not just a Doppler effect, like the sound of a siren. In an expanding universe, the wavelengths of light grow as the space they travel through grows. The light remembers the whole path, not just the motion of its source. Bring this back to the human scale, and the tone stays gentle. We cannot feel ET change in our hands. Local bonds and local gravity keep tables solid and planets in orbit. Expansion wins only across great stretches where nothing else ties things down. What we can do is read the light, one careful step at a time, and let it sketch the curve that tells the story. From that curve, we learn that the universe once slowed under gravity's pull, then turned to a fresh widening under dark energy's push. We see that the mix today is mostly an invisible pressure that does not clump, some unseen matter that does, and a small slice of ordinary atoms that make stars and people. There is one more twist waiting just ahead in the tale, the part where a famous mistake points the way. Long before supernovas revealed acceleration, Einstein added a term to his equations to hold the universe steady, then later called it his blunder. That same term, reinterpreted, now looks very much like dark energy in mathematical clothing. The scale factor carries that story neatly, a small, constant push woven into the fabric itself. whether it is truly constant or only appears so for now, remains one of the great open questions. For the moment, the curve, ERT, gives us a shared map, a clean way to translate redshift into time, distance into history, and the glow of dying stars into a quiet account of how the universe grew and how it will continue to grow, steady as breath, into more of itself. Einstein met a strange crossroads where theory pointed one way and the sky, as people then read it, seemed to point another. His new equations of gravity, the smooth geometry of general relativity, said a universe could not simply sit still. The math wanted motion, either a gentle swelling or a slow collapse. Yet the common wisdom of the time pictured a calm, eternal cosmos, steady as a painting on a wall. Trusting the observations, Einstein adjusted the math. He added a quiet term, the cosmological constant lambda, a soft pressure woven into empty space. Its role was delicate, just enough outward push to balance gravity's inward pull, like two children on a seesaw holding perfectly still. With that, a static universe seemed possible again. For a while, the idea fit the mood of the era. Then the evidence shifted. Edwin Hubble and his great telescope on Mount Wilson showed that distant galaxies are receding, and that farther means faster. The universe was not fixed. It was expanding, just as Einstein's unaltered equations had said from the start. Einstein set the extra term aside and later joked that it had been his greatest blunder, trusting the picture on the wall rather than the math in his hands. Decades passed, and the sky offered a quiet twist. In the late 1990 seconds, light from faraway supernovas arrived dimmer than a steady or slowing expansion could explain. The universe was not only expanding, it was speeding up. Something was giving space a constant, gentle shove. The simplest name for that shove was the one Einstein had already written down: a cosmological constant, a uniform energy of the vacuum itself, everywhere the same, with gravity's sign reversed. What had been called a blunder looked like foresight. If the vacuum carries a small, steady energy, it does not pile up into stars or dust. It stays smooth, filling space evenly, acting as a faint pressure that quickens expansion. The number is tiny when written per cubic centimeter, about a 10 billionth of a joule. But the universe has so many cubic centimeters that the total dwarfs all starlight, gas, and dust combined. The term that once held the universe steady in Einstein's static dream now guides the late-time story of how it opens. Behind that elegant fit lies a deep puzzle that Einstein did not face. If the vacuum holds energy, how much should it hold? Quantum field theory, our best language for subatomic physics, adds up the restless flickers of every field and hands us a number that is wildly too large, larger than the observed value by something like 1 followed by 120 zeros. If that estimate were right, space would rip outward so ferociously that galaxies could never have formed. Since galaxies exist, our sum is missing a cancellation, or our picture is incomplete, or both. Maybe some mechanism hides almost all of the vacuum's energy, leaving just a thin residue to drive today's acceleration. Maybe dark energy is not a constant at all, but a field that drifts slowly with time, borrowing traits from the vacuum without inheriting its catastrophic total. For now, the simplest, steadiest option, the cosmological constant, matches the data best, even as the underlying why this small and not that large remains one of physics' quiet riddles. The thread of observation that pulled the constant back into the story began with careful nights on a mountain. Hubble's first task was to settle what spiral nebulae really were. By tracking Cepheid variable stars, their predictable brightening and dimming, he measured their distances and showed those spirals lay far beyond the Milky Way. The universe grew from one city of stars to a country of cities beyond counting. Then came the second plot. Distance on one axis, redshift on the other. The points lined up in a simple pattern. Farther meant faster. At first, it looked like motion through a still room, as if every galaxy were fleeing a central blast. That would have put us in a special seat at the center. And that did not sit well. The better picture was gentler. The room itself was growing. Galaxies were raisins in a rising loaf. The farther two raisins sit apart, the faster the dough pushes them away from each other. No raisin is at the center of the loaf. The loaf is all there is. Hubble's relationship became our first measure of a global property of space, the expansion rate, later named the Hubble constant. His early value, thrown off by misidentified stars and calibration errors, made the universe look too young, only a couple of billion years younger than Earth's rocks. The methods improved, distances grew, and the age of the cosmos widened to a comfortable span. The core relation remained. From a handful of nearby galaxies to the most distant we can see, distance and redshift march in step. This simple graph made cosmology possible. Before, astronomy mapped a sky, angles and brightnesses, a dome with lights. After, we began to map a volume, a living history of distances and times. The expanding universe became the backbone of the Big Bang story. A hot, dense beginning, cooling with time, structure growing from small ripples into galaxies and clusters, and, much later, a turn toward acceleration as vacuum energy took the lead. To thread Einstein's constant back into this flow, it helps to hold a few images in mind. The cosmological constant is not a wind that blows from somewhere. It is a property of the room itself. Think of a spring sewn into the fabric. Its gentle pull constant per patch of cloth. As the fabric stretches, the spring's influence does not dilute. It is the same everywhere and every when. That is why a constant vacuum energy makes expansion accelerate. The larger the room becomes, the more total push is at work, even though the push per unit room stays the same. Now return to Einstein's choice in 1917 and the weight of hindsight. He had a theory that, when left alone, pointed naturally to a changing universe. The sky he trusted looked fixed. He added a term to hold it still. When the sky later revealed its motion, he dropped the term and called the addition a mistake. Today's sky leans on that same term to explain its late-time quickening. The arc from blunder to backbone is not a neat circle. It is a reminder that science moves by listening to both math and measurement, letting each correct the other, and forgiving past turns when new paths appear. The deeper irony cuts one step further. Even if the cosmological constant is the right description of dark energy, the old calculation from quantum theory says the vacuum's energy should be unimaginably larger. Why that raw total is almost perfectly cancelled, leaving only a whisper, is an open door. Perhaps the cancellation is a clue to a new symmetry we have not found. Perhaps the constant is not constant but only looks that way over the times we can measure. Perhaps the vacuum structure is not what we think, and our sum double counts a landscape that is more spare than it seems. Each perhaps is an invitation to gentler, more careful experiments and to theories that risk new shapes. While the constant sits quietly in the equations, the human story that brought it back runs through the same mountain night where Hubble watched. Imagine the ritual of those observations. Long exposures on glass plates, stars and smudges, slowly imprinting their light. Careful measurements of positions and periods. Stacks of numbers turning into points on paper. The first distances pushed outward across a gulf no one had crossed. The redshifts lined up. The line on the graph made a sentence. The universe is expanding. We were not in a privileged seat. We were in a rising loaf. That single sentence loosened dozens more. If space expands, it must have been smaller. If it was smaller, it was hotter and denser. If it was hot and dense, light and matter must have been tied together, then later parted. Somewhere in the sky, we should find the cooled echo of that bright time. We did. A faint microwave glow surrounds us, almost perfectly smooth, with tiny ripples that later grew into everything we see. Each line of evidence touched the others, and the picture came into focus. Hubble's law also nudged a question that poets and physicists both ask. Where is this heading? A straight line, left to itself, would have meant a steady pace. A curve bending down would have pointed toward gravity slowly winning. The actual curve bends up. The constant in Einstein's equation, once set aside, came back as the simplest way to fit the bend. Dark energy would then be less a new thing than a new name for a term we already knew how to write. Today, different methods disagree about the exact value of the expansion rate, but not about the acceleration. The Hubble tension is a stubborn 6% scale mismatch between local measurements that grow from the distance ladder and global measurements read from the baby picture in microwaves. The tension could be a quiet flaw in one rung or another. It could be a whisper of new physics, perhaps a small change in the way energy moved in the early universe that shifts the calibration of the whole curve. Whatever the answer, the constant's role stays steady in the current best picture. A small, uniform energy of the vacuum guides the late time widening. If you set the numbers down and listen to the tone, the lesson is simple and kind. We live in a universe that once slowed under its own weight and now speeds up under a faint pressure sewn into emptiness. The term "a single mind," added to hold the sky still, reappeared as the key to its growing pace. A mountain telescope, steady hands, and a line on a graph turned a two-dimensional dome into a three-dimensional, time-rich map. The constant, the expansion, the glow of the early sky, each has a voice. Together, they sing one slow song. And yet, for all the grandeur, the nearby world stays familiar. Tables do not stretch. Planets keep their orbits. Galaxies hold together where gravity is strong. The cosmological constant works on the large and the long, not the small and the near. Its pressure is too smooth and too slight to loosen what local forces bind. It writes in the margins of the largest pages, moving the story forward by widening the space between the chapters. From here, gentler questions rise. Is lambda truly constant, or does it drift with time by some small amount we have not yet learned to hear? Is the vacuum's whisper the shadow of hidden fields, or the top note of a deeper structure that makes space itself? Could the tension in the expansion rate be the first hint of that deeper score? Each question adds a thread to the tapestry and points us back to the same practice. Gather better light, measure more carefully, fit the scale factor with a steadier hand, and let the sky correct us when our pictures grow too tidy. Einstein's blunder is now a lantern. It reminds us that even wrong turns can light the next bend in the road, that equations can be wiser than our first readings, and that the universe often gives back what we thought we should discard. The constant in his field equations, tiny, steady, and everywhere, speaks softly. In that softness, it has come to guide the late-time fate of everything we can see. We read it in the dimming of far supernovas, in the smoothness of the ancient glow, in the spacing of galaxy clusters across the dark. We carry it forward in it, the calm dial that tells us how the ruler changes with time, and we live our days within its story, under a sky that is not static after all, but opening slowly, patiently, into more of itself. Picture the universe as a long, quiet race between two steady forces. One is expansion, a soft, persistent widening that carries galaxies apart. The other is gravity, the gentle pull that tries to gather everything back together. Which one wins depends on how much stuff the cosmos contains. There is a precise tipping point called the critical density where the balance is perfect. Add a little more matter and gravity eventually turns the expansion around. Take a little away and space keeps widening forever. Strangest of all, that tipping point is tiny by everyday standards. Roughly 5 hydrogen atoms in every cubic meter of space. Almost nothing. And yet it sets the fate of everything. You can feel the logic. Expansion spreads matter out, thinning it across growing volumes. Gravity works best when matter is close and dense, so as the universe stretches, gravity's hand weakens. If the average density were higher than the critical value, gravity would slow the widening, bring it to a stop, and lead to a fall back inward, a big crunch. If the density were lower, expansion would never quite be caught. In the knife-edge case, the cosmos would coast forever, slowing toward a halt but never stopping, like a ball tossed upward with just the right speed to climb endlessly while its pace crawls towards zero. For decades, the holy task was to measure the density, count the matter, divide by the volume, declare the future. But the sky refused to be simple. Galaxies spun too fast at their edges. Stars in the outskirts orbited as if there were far more mass than their starlight announced. The missing weight became dark matter, invisible stuff that does not glow or absorb light, yet tugs by gravity. By every clue we could gather, dark matter outweighs ordinary atoms by more than 5 to 1. Include it, and the ledger comes to only about 30% of the critical density. That would mean endless expansion, and, in the far future, a quiet thinning to near nothingness. Then a new actor stepped on stage. The light from distant supernovas, the baby picture ripples in the cosmic microwave background, and the spacing of galaxy clusters all pointed to the same surprise. Expansion is accelerating. Something smooth and persistent dark energy acts like a gentle pressure sewn into space itself, a negative pressure energy that makes gravity push instead of pull on the largest scales. With dark energy in the mix, the simple idea of critical density changes flavor. It is no longer just how much stuff, but also what kind of stuff. Our best reading today is a universe that is about 68% dark energy, 27% dark matter, and 5% ordinary matter. In that blend, the total energy density sits very near the critical value, leaving space almost perfectly flat in its geometry. That closeness raises the flatness problem. Why should the universe be so exquisitely near the balance point? In most simple models, density quickly runs away from critical, either too high, leading to collapse, or too low, leaving a thin, empty world. Keeping so close for billions of years seems like an impossible aim unless something in the early universe set the target. The leading answer is inflation, a brief, ferocious growth spurt in the first sliver of a second. Inflation stretches any initial curve in space so flat that the universe emerges with a density effectively pinned to the critical value. The later, gentler expansion keeps that near flatness intact. Even with inflation, another coincidence peeks through. We are living in a narrow window when dark energy, dark matter, and ordinary matter all matter in roughly comparable ways. A few billion years ago, matter ruled and expansion slowed. A few billion years from now, dark energy will rule completely, and the widening will look almost pure and exponential. Why do we happen to see the universe during this brief handoff? One quiet answer is selection. Complex observers need heavy elements, steady stars, and time for chemistry and life to emerge. Those needs favor eras when matter has had time to form galaxies and planets, but before the sky thins beyond usefulness. In that view, we notice near-critical conditions, because only near-critical worlds can host beings who notice. That is the modest, single-universe story. Some ideas invite a larger stage. In eternal inflation, the early growth spurt never fully ends. Quantum jitters keep sparking new bubble regions that each begin their own hot starts, their own big bangs. Our observable universe would be one bubble among many in a vast inflating background. Each bubble cools and evolves under its own settings, with slightly different amounts of dark energy, different balances of matter, perhaps even different low-level rules. Some bubbles might expand faster than ours because their dark energy is stronger. Others might expand more slowly because their matter is denser. A few might already have collapsed in brief, big crunches. Others could be racing toward big rips. Most would be sterile. A rare few might be friendly to structure and life. The idea stretches still further in another corner of physics, where the many worlds interpretation of quantum mechanics imagines that every measurement branches reality into different outcomes. In that story, Parallel universes are not faraway places, but neighboring branches of possibility, each carrying its own history forward. These two notions, the bubble multiverse from inflation and the branching from quantum theory, are not the same. One lives in cosmic space, the other in the book of outcomes. But both whisper the same unsettling thought. What we call the universe may be only one thread in a wider weave. It is important to keep the tone calm here. Multiverse ideas are working theories, not settled fact. By design, most bubbles would be forever unreachable from ours. No light could cross the inflating sea between them. Many worlds is a way to read quantum math that fits experiments, but is not the only way to read it. Still, these pictures can soften the sting of coincidence. If there are countless tries, some bubbles will land close to critical density. Some eras will line up so that matter, and dark energy share the stage. We find ourselves on one such stage because it is one of the few where an audience can form. Step back to the quiet, measurable part of the tale. On the largest scales we can map, space looks flat to exquisite precision. The total energy density is very near the critical value set by Einstein's equations once dark energy's effect is counted. Dark matter bends light and steers the rotation of galaxies. Dark energy bends the history of expansion. Inflation explains why the early universe started so smooth and close to balance. Later growth explains why structures could form at all. Put together, the story is not one of a coin landing on its edge by luck alone, but of early conditions and steady rules that make the edge wide enough to hit, and of observers who can only appear where the edge holds. The future follows from the mix. With dark energy in command, expansion will not reverse. Gravity will keep local structures bound, our Milky Way and its neighbors merging into a quiet island of stars, but the wider web will drift beyond sight. The average density will fall further below the critical value for matter, while the total, including dark energy, continues to trace a flat geometry. Heat death waits a very long way off. The path there is slow and even. Between now and then, the universe stays what it has been for a while. A place where the balance is near perfect, the geometry is almost flat, and the great race between widening and gathering has a clear but gentle winner. That we live during the brief moment when the contestants run side by side may feel uncanny. Held lightly, it is also a comfort. The conditions that let you read these words are the same ones that let stars burn and elements form, that let gravity build homes for light, and that let a thin, near-empty universe be just full enough. Imagine reality as a great tree that keeps sprouting new branches. At every moment, a fresh branch splits off, carrying a universe that expands in its own way. Many look almost the same as ours, changed only by tiny quantum flips, too small to notice. Others drift far from our path because those small flips led to very different chains of events. In some, dark energy is stronger and the expansion runs faster. In others, dark energy is weaker and gravity may someday bring the widening to a halt. If the branching never ends, then every possible story of expansion is acted out somewhere on that tree. That picture has a personal echo. On some branches, a version of you watches the sky fade toward heat death. On others, a different you lives in a world racing toward a big rip. In still others, the cosmos turns back on itself and collapses. The expansion of space would then touch every possible path your life could have taken across worlds you will never meet. This raises a hard question. If there are endless branches, does the fate of our single world matter? Some people say the multiverse makes any one ending unimportant. Even if our sky grows cold and quiet, other versions of you go on in other branches, under other skies. Others answer that each universe still matters to the people inside it. Meaning is local. Your sky, your choices, your hopes, and the way your space grows are real here, whether or not there are copies elsewhere. The idea of many universes also reshapes the word expansion. In a single world, expansion means all space grows. In a multiverse, it might mean only our layer grows, while a larger structure stays the same. Or the larger structure could be expanding too in ways that do not fit our usual ideas of space and time. We might be watching a small tide inside an ocean we cannot imagine. Could we ever find signs of other bubbles? Astronomers have looked for subtle marks in the cosmic microwave background patterns that a past collision between universes might leave behind. So far, nothing stands out. But vast scales and faint effects work against us. The lack of a signal does not prove there are no neighbors. It may simply mean the clues are too soft to hear with tools we can build. We may be left to wonder, forever, about other branches we can name but never touch. Even without parallel worlds, our own expansion sets deep puzzles about information and meaning. Everything you are lives in patterns. The way neurons connect, the way molecules sit, the way atoms line up. These are arrangements in space. As space grows, those arrangements stretch, thin out, and drift. Over long enough time, the pattern that makes your memories and your you would spread so far that no process could knit it back together. Identity becomes a faint mist in a very wide room. Physics pushes back with another idea. Information cannot be destroyed. This is where the holographic principle enters. It says that all the information inside a region might be stored on the surface that wraps it, like a picture hidden in a thin film. If that is true, then as space expands and surfaces grow, the capacity to store information also grows. The universe could hold more detail, more pattern, more story, even while old patterns are stretched thin. That is both comforting and tricky. The patterns that make a mind are precise. They depend on where molecules sit and how signals move. As expansion goes on for ages, those exact details drift apart. Yet quantum mechanics adds a twist. Quantum states can depend on relationships, not locations. Entangled particles remain linked no matter how far apart they are. Their shared state can outlast the separation. If information lives in those relationships, some patterns could, in principle, persist even as matter spreads. Still, expansion sets a hard limit. Regions that now trade light and messages will someday slip beyond each other's reach as space grows between them faster than light can cross. They become causally disconnected forever, out of touch. Information then gets trapped in separate islands. Each island holds only a finite store that will never meet its siblings again. That looks like a kind of loss, even if, strictly speaking, nothing is erased in the global book of quantum rules. Maybe the way out is to look at more than one scale at once. Local patterns fade, but cosmic patterns grow. The universe keeps its own diary, in the faint afterglow of the Big Bang, in the web of galaxies, in the way space-time curves. The full expansion history is written into these large structures. That record outlives many small stories, like sediment layers that keep the shape of a vanished river. Yet even cosmic memory is not safe from acceleration. As dark energy keeps stretching space, the ancient microwave glow will be pulled to wavelengths so long that no future instrument could ever detect it. Far-off civilizations may see no sign of a beginning at all. No echo of a hot, dense past. No hint that the sky once blazed. They might conclude the universe is small, static, and eternal. The proof of their true history would be beyond reach, erased not by fire, but by distance. So we circle back to meaning. If expansion eventually hides all records, do past events still matter? One gentle answer is that value lives in the living, not only in the archive. A melody matters while it plays, even if the last note fades. The brief arrangements that rise during this widening stars, minds, languages, kindness, earn their place by existing, not by lasting forever. Their worth is in the warmth they hold for a time. Of course, even that comfort depends on there being someone to feel it. If the universe widens until no observers remain, who is left to care? This is the sober edge of the story. The far future may be empty of witnesses, but emptiness ahead does not empty the present. We are here now, in the small span when the sky is readable and the light is still arriving. We can understand a little of how space grows, and why patterns form, and how information threads through matter and time. Whether there are countless branches or only this one, whether the diary is readable forever or not, we can keep our eyes open while the pages turn. Expansion does not make meaning impossible. It makes it precious. It asks us to notice, to learn, to share, and to leave gentle traces for as long as the room allows. Then, when the room grows too wide for voices to carry, the stories we told will have been true while they were told, bright for their moment, and part of the long, patient widening that holds us all. Imagine the night sky, 150 billion years from now. Astronomers will step outside, lift their eyes, and see a universe that looks nothing like ours. Most galaxies will have slipped beyond the cosmic horizon. Their light will be stretched to such long waves that no instrument can catch it. From that far future, those galaxies won't appear dim, they'll simply be gone. Only our small neighborhood will remain. The Milky Way and Andromeda, along with their companions, will have merged into one huge, quiet, elliptical galaxy. A few dozen dwarf galaxies may circle it like fireflies. To the scientists living then, that island will look like the entire universe, a lone city of stars floating in endless dark. The clearest clue we have today, the cosmic microwave background, will be gone too. Expansion will pull that ancient glow to wavelengths larger than the observable sky itself. Future telescopes will find no leftover warmth from the beginning, no soft hiss from a hot, young cosmos. The redshift distance pattern that revealed expansion to us will also vanish. With no far galaxies to measure, there will be no Hubble's law to discover. Their universe will seem small, static, and eternal. Those careful observers will do what good scientists always do. They will measure, compare, repeat. Their methods will work perfectly. Their data will be honest. And yet their best theories may be wrong, because the key evidence will have slipped out of reach. They may decide their single, giant galaxy has always existed, alone in a changeless void. They may never imagine the crowded, racing universe we see today. Even the fingerprints of the first elements will be faint. The nuclear reactions that forged hydrogen and helium long ago will be readable only in old, dying stars, if any are left to read. Those future thinkers will face a quiet problem of knowledge. Not a lack of intelligence, but a lack of clues. It is a reminder to us, here and now, to hold our own confidence gently. Are there signs early civilizations could have seen that we will never recover? Is the universe showing us only what this era allows? Follow the clock further and the room grows emptier still. Gas will thin until new stars cannot form. Old stars will burn out. Planets will cool. Black holes will slowly fade by Hawking radiation, turning their mass into a trickle of particles. The cosmos will move toward heat death near perfect uniformity, near perfect quiet. If anyone could witness that final hush, they would see almost nothing. No clusters, no galaxies, no stars, a few particles drifting through almost absolute night. From that view, it would be impossible to guess that the universe once held trillions of galaxies, or that life once asked questions under warm skies. The history would be true, but the evidence would be gone. All of this loops back to the question that started our journey. What is the universe expanding into? The words feel natural, because everything in daily life needs an into. A balloon swells into the air. A city spreads into the countryside. A puddle grows across a sidewalk. But the universe is not inside a larger room. It is the room. When space expands, it does not push into something else. It makes the very idea of something else by growing. Asking what the universe expands into is like asking what lies north of the North Pole. North stops at the pole. The word loses its meaning beyond it. In the same way, into assumes an outside that does not exist for the universe. Space is not expanding into a container. It is creating the concept of a container as it expands. This isn't a trick of language. It is how reality seems to work. Before expansion, there is no outside. Expansion doesn't just add more space. It builds the logic that makes here and there possible. The universe expands by becoming more universe, not by growing into non-universe. Think of it like this. If you ask, what caused the first cause? Or, what holds the container of everything? You've stepped past the edge of the map. You're using ideas that only make sense after the thing you're asking about already exists. The same is true for expansion. The universe is not traveling toward a destination. It is unfolding possibility. That shift turns the story from a machine into a mystery. Expansion is not just the ruler getting longer. It is reality booting itself up, one new bit of space at a time. Each fresh patch of room offers a chance for matter to arrange itself, for stars to light, for chemistry to dance, for minds to wonder. The universe is not expanding to reach some finish line. It is expanding to make room for what can be. Where does that leave us? Not as passengers sitting in the back of a cosmic bus, but as part of the engine. We are built from the same fabric that widens the sky. Our questions, our instruments, our late-night thoughts are the universe turning toward itself with curiosity. When we ask what the universe expands into, that very question is the universe doing what it does, creating new patterns, testing new ideas, making meaning for a while under a changing dome. This view also softens the worry about endings. If the far future holds silence, that does not erase the music now. A song matters while it plays. A flame matters while it burns. Galaxies, oceans, languages, friendships, each is a shape the universe tries on for a time. Their worth is not in how long they last, but in the simple fact that they can arise at all. And yes, the future may hide the past from new eyes. That is a loss, but it is also a lesson. Understanding is always local to a moment. We know what we can with the light that reaches us, using tools we build in the time we're given. The best we can do is listen well, check our pride, and leave good records for the next minds who look up. So the answer, tucked in plain sight, is quiet and wide. The universe does not expand into anything. It expands by making the notion of into possible. It expands into mystery and wonder, into more questions, more patterns, more room for minds to wake up and notice. We are not outside that process, peering in. We are inside it, made of it, helping it along each time we measure a faint glow, trace a galaxy's curve, or share a thought in the dark. Even if, someday, no observers remain, the fact that questions were asked will have been true. For a time, the universe turned itself into people who could name the stars and argue with the night. For a time, it made telescopes and songs. For a time, it learned to say, gently, that there is no wall to grow into, only a fabric that keeps weaving, steady as breath, into more of itself. That is where the question leads. In the end, not to a doorway at the edge of space, but to a deeper way of seeing. The universe expands by being the universe. We are pieces of that widening, brief and bright, honored to watch and to wonder while the room grows wide.